What specific problem does the Affine concept editing ACE method aim to solve, and how does this relate to the previously established techniques of directional ablation and activation addition?
The Affine concept editing ACE method aims to solve the problem of generating nonsensical outputs in models when steering behaviors, particularly in the context of refusal. This issue arises from the limitations of existing techniques like directional ablation and contrastive activation addition, CAA, which either fail to standardize behavior across different inputs or can lead to unpredictable outputs. ACE generalizes these methods by incorporating an affine decomposition that allows for a more deterministic control over the degree of behavior exhibited, addressing the ambiguity in the linear representation hypothesis. By setting a reference point for behavior, ACE ensures that the steering parameter directly influences the model's output in a coherent manner, unlike directional ablation, which can lead to nonsensical results. Thus, ACE combines the strengths of both directional ablation and activation addition while correcting their shortcomings, resulting in improved standardization and coherence in model outputs.
Can you explain in detail how the proposed method of affine concept editing works? Please illustrate the steps involved in this process clearly and methodically.
Affine concept editing, ACE, is a method that combines corrected directional ablation with contrastive activation addition to achieve more standardized steering of model behaviors. The process begins by defining a reference point, v_0, which represents a standardized degree of behavior and a direction vector, r, that corresponds to the target behavior. The activation vector, v, is then decomposed into three components: the displacement from the reference point, v_0, the projection of this displacement onto the orthogonal complement of r, and a term, alpha r, that indicates the degree to which the behavior is represented in v. To implement ACE, we first determine alpha_0, such that alpha_0 r equals text project r caret parallel v_0, ensuring that when alpha equals 0, the mean expression of r is set to a known quantity. Next, we choose r to ensure that the expected values of the steered activation vectors align with the means of known samples for both null and target behaviors. Finally, the resulting technique allows for deterministic control over the behavior exhibited by the model, effectively steering it without leading to nonsensical outputs, as demonstrated in experiments with Llama 3 and Hermes Eagle RWKV-V5.
Could you provide a simple and illustrative example of affine concept editing in action, detailing how the modifications to the activation vector are made?
Affine concept editing, ACE, modifies the activation vector by combining elements of contrastive activation addition, CAA, and corrected directional ablation. For instance, consider an activation vector, V, that represents a certain behavior, and we want to steer it towards a refusal behavior. First, we establish a reference point, v_0, that corresponds to a known degree of non-refusal behavior. The activation vector is then decomposed as v equals v_0 plus text project r caret perp, delta v plus alpha r, where delta v is the displacement from v_0, and alpha is the degree to which the target behavior is represented. By adjusting alpha to a new value, alpha, we can effectively steer the model's behavior towards refusal while ensuring that the resulting activation vector remains coherent, thus avoiding the nonsensical outputs that can occur with other methods. This process allows for a more standardized control over the model's behavior compared to previous techniques.
What are the theoretical or practical benefits of implementing the ACE method over existing techniques, particularly concerning the performance of large language models?
The ACE method offers significant theoretical and practical benefits over existing techniques like contrastive activation addition, CAA, and directional ablation. Theoretically, ACE generalizes the linear representation hypothesis by incorporating an affine decomposition, which allows for a more nuanced understanding of how behaviors are represented in activation space. Practically, ACE provides superior standardization in steering behaviors, as demonstrated in experiments with Llama 3, where it effectively controls refusal behavior without leading to nonsensical outputs, a common issue with directional ablation. Additionally, ACE allows for deterministic control over the degree of behavior exhibited, ensuring that setting the steering parameter to 1 induces the desired behavior, and 0 induces null behavior, which is crucial for applications requiring precise model behavior. Overall, ACE addresses the shortcomings of previous methods by combining the strengths of both CAA and directional ablation, leading to more coherent and reliable outputs in large language models.
How did you validate the effectiveness of the ACE method in your experiments? Please specify the experimental design, datasets used, and performance metrics that demonstrate its efficacy.
To validate the effectiveness of the Affine concept editing ACE method, we conducted 2 experiments focusing on steering refusal behavior. The first experiment utilized the Llama 3 model, where we compared ACE's standardization effect against that of contrastive activation addition (CAA). The second experiment was performed on the Hermes Eagle RWKV v5 model, where we assessed the coherence of the text generated by ACE in contrast to the nonsensical outputs produced by directional ablation. Performance metrics included the probability of refusal across a range of steering parameters, evaluated using Llama 370B Instruct as a scoring model to determine whether prompts were refused. Results indicated that ACE achieved superior standardization in Llama 3 and produced coherent outputs in Hermes Eagle RWKV v5, demonstrating its efficacy in controlling refusal behavior effectively.
What limitations did you encounter with the ACE method in your findings, and how do these limitations impact its generalizability and practical applications?
In our findings, we encountered limitations with the ACE method regarding its standardization effect, which, while superior to contrastive activation addition (CAA), was not perfect. Specifically, we observed that ACE parameters slightly below 0 and slightly above 1 yielded the most effective results, indicating that the derived steering vectors may be flawed or that directional ablation does not completely erase information. This imperfection in standardization suggests that ACE may not consistently control the degree of behavior across different models, impacting its generalizability. Additionally, preliminary experiments with more sophisticated erasure techniques, such as LEAS, did not enhance the standardization effect and were detrimental in some cases. Consequently, these limitations highlight the need for further research to explore whether linear or nonlinear techniques can reliably erase concepts like refusal and to extend ACE's applicability to a broader range of behaviors.